Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar focuses on a multi-species evaluation of hibernation physiology and influence on risk factors associated with the white nose syndrome, a fungal disease responsible for killing millions of hibernating bats in Northern America. Dr. Sarah Olson of the Wildlife Conservation Society will discuss data, analyses, and tools to test the hypothesis that species-level bioenergetic traits and environmental factors contribute to differential mortality due to the white nose syndrome among these bat species. Dr. Olson will pause midway through her presentation to answer questions, and we will conclude the webinar with a longer Q&A session. The next several slides provide instructions on how to optimize your webinar experience. If you have not done so already, please download Zoom at the link shown here and also provide it to you in your webinar registration confirmation email. If you're unable to download Zoom, you can view the slides using a compatible internet browser, such as Firefox, IE, or Edge, and by creating a free Zoom account. If you're unable to view the slides, or if you have issues with your screen getting frozen, please try keying in Control and F5 to perform a hard refresh of your screen. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and please follow the prompts as they appear on your screen. If you continue to have difficulties, call into the conference line shown here. You can also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. All questions should go to the Q&A option, and the chat box should be reserved for communicating with our host today for technical difficulties. And if you continue to have problems, just download a PDF of the slides from the webinar webpage. It is available for download right now. And that way you can call into the conference line provided to you in your webinar registration confirmation email and follow the presentation using a printout of the PDF. Note that we will also be live streaming the webinar on the SERDP ESTCP YouTube channel link shown here. So that's another option for following along. Today's broadcast will be listen only. Please submit questions by using the Q&A box on your screen. Do not wait until the Q&A period to submit your questions. We do encourage you to submit them as you think of them. And when you do submit them, please make sure to add your organization name at the end of your question so that we can identify you. With that, I would like to introduce Dr. Kurt Preston, who is the SERDP and ESTCP Program Manager for the Resource Conservation and Resiliency Program area. Dr. Preston has tracked his career between civilian, university, and military positions. Prior to his current position with SERDP, Kurt was a faculty member and research administrator at the University of Nebraska-Lincoln, where he led faculty development efforts to improve research competitiveness. In this position, he also worked with technology transfer personnel, academic departments, and colleges to build university research capability. In addition, Dr. Preston has served as a member of Chief of the Army Corps of Engineers Environmental Advisory Board. Kurt, please proceed.
Wow, thank you, Rula, and I'm happy to welcome everyone today to the SERDP and ESTCP webinar series. So SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the Department of Defense, the Department of Energy, and the Environmental Protection Agency. SERDP's mission is to identify and address high priority environmental science and technology opportunities that focus on DoD, Department of Defense requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP and or other research programs and are designated and designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP and 5 in ESTCP. The Installation, Energy, and Water program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapons Systems and Platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Resource Conservation and Resiliency program area, which has essentially 3 main areas of research: natural resources, resiliency, and wildland fire. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, and those topics will include abiotic degradation of chlorinated solvents in subsurface environments, approaches for managing contaminated sediments, improving energy efficiency through advanced building controls, approaches for PFAS sampling and treatment, and others. The next resource conservation webinar will be offered on March 11th, 2021, and will address new resource conservation paradigms on Department of Defense lands. You can find additional information about upcoming webinars at this link. And I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you can please take a moment also to complete the survey that will pop up on your screen at the end of this webcast. Finally, I would like to remind you that registration is open for the 2020 SERDP and ESTCP Symposium. This year it's a virtual event and will showcase the latest technologies that enhance the Department of Defense mission through improved environmental and energy performance. Finally, I sure hope that you enjoy the webinar today. Thanks.
Thank you, Kurt. It is now my pleasure to introduce today's speaker, Dr. Sarah Olson, who is the Associate Director of Epidemiology for the Wildlife Conservation Society Health Program. Although that program is based out of the Bronx Zoo in New York, Dr. Olson is physically based out of Montana. Her ongoing research efforts focus on assessing the risk of white nose disease syndrome to North American hibernating bats, tracking human health threats associated with wildlife trade in Asia, establishing national wildlife health surveillance platforms, and researching the disease ecology of filoviruses in Central African fruit bats. In addition to leading scientific studies, Dr. Olson provides research support to field vets and conservation staff around the world on wildlife health threats and diseases, with a focus on promoting the understanding of conservation impact of frontline wildlife diseases, building One Health capacity, and translating science into effective and lasting interventions. She received a bachelor's degree in microbiology and another one in German from Montana State University, and a joint doctoral degree in population health and environment from the University of Wisconsin in Madison. Sarah, we're so happy to have you. Please proceed.
Thank you, Rula, for that kind introduction and for this great opportunity to present our project and findings from a 4-year study that assessed white nose syndrome threats to Western bat species. I can't say enough that a couple folks were really instrumental to this project, and these were my co-PIs and key collaborators, Leah McGuire, Nate Fuller, Emma Kunkel, and Emily Johnson at Texas Tech University, Raina Plowright, Katie Haas, and Dan Crowley at Montana State University, Brett Dixon and Meredith McClure at Conservation Science Partners, David Heyman, Reed Hernack, and at Massey University in New Zealand, Corey Lawson, Yvonne Zahl, Corey Olson at Wildlife Conservation Society Canada, Craig Willis at University of Winnipeg, our field tech, Kirk Silas, and all of our field partners and co-authors. Let me get this slide to advance here. Oh, it was advancing. All right. Come on. There we go. Okay. Now it's talking. Here's the outline for my talk today. I'll first provide background on white nose syndrome, which I'll abbreviate as WNS in my slides, and its impact on hibernating bats, and then explain our project's overarching objectives, which focused on filling Western bat knowledge gaps and risk factors related to white nose syndrome. I'll then cover our methods related to data collection and present our empirical finding results and conclusions, as well as the benefits of that work to the DoD. And I'll wrap up the first part of the talk with a Q&A session at about halfway through, just on those empirical findings. In the second half, the focus will shift to the results, conclusions, and benefits of the data modeling side of the study, with an additional Q&A session at the very end. So the DoD's mission requires maintaining access to diverse training environments. However, this access can be restricted due to endangered species protections. The DoD is committed to stewarding conservation on installations and preventing listings if and when possible to avoid impacts on military readiness. And in 2016, they recognized there was an important knowledge gap about ecological factors needed to better manage disease threats to species of concern. So our project focused on bats and white nose syndrome. Why should we keep bats around? That's a good question. Last I checked, there were 1,421 species of bats known to science, and the ones I'll be talking about today play important ecological roles in their landscape. They are also a fascinating area of emerging research into immunology, physiology, and even cancer. They just do things differently, and that can inform future scientific discoveries in these fields. In terms of economic value, they play a huge role in consuming the insect pests of agricultural crops. It's estimated bats save the U.S. agricultural industry around $22 billion a year in pesticide costs. Just one colony of big brown bats consumes 1.3 million insect pests per year. What is white nose syndrome? So these images show the scenes of dead bats that have succumbed to the disease in eastern United States. In a period of 6 years, it's estimated that 6 to 7 million bats were killed. Mortality has ranged from 30 to 99% at infected Hibernacula. The pathogen is a cold-loving fungus called Pseudomonas destructans, PD, or P. destructans for short. This species of fungus is also found in Europe, and regional extinction has been predicted for Myotis fucus, the little brown bat, the species showing the highest mortality in the East, and at least one species in the US, Myotis septentrionalis, has been listed because of white nose syndrome. Now, despite the morbid images in caves, this disease is not uniformly lethal, and mortality rates have been mixed among eastern hibernating species. Therefore, more research is needed to better understand patterns of white nose syndrome vulnerability. This is a conceptual model of white nose syndrome spread. We can start there at the center. The focus is not, or the fungus is not reliant on hibernating bats for survival or growth, and it can persist in cold cave environments. It grows best typically between temperatures of 7 and 16 degrees Celsius. So the new hosts are inoculated by either contaminated caves, or wherever they're hibernating, or by bats carrying fungal spores. And once infected, this leads to fungal growth on bat tissues, leading to what's, the typical white nose, but there are also white wings. And once infected, this leads to fungal growth on pretty much all bat tissues. And this triggers physiological effects and further onward transmission to other cave sites in bats. So national and state agencies have already put protocols in place to limit anthropogenic transport between contaminated and uncontaminated sites. But there is a theory and evidence that physiological effects end up determining whether a bat survives or succumbs to disease and the degree to which a bat is actually a vector for fungal spores. Therefore, the physiological effects are really critical to understand spread and were central to our study. So bats end up dying from the physiological impacts of this pathogen. Bats hibernate in cool environments, which are ideal for this fungus's growth, and they go into a state of torpor with significantly reduced body temperatures. When hibernating, they're typically just a few to several degrees above freezing. In laboratory studies, bats infected with the fungus have more evaporative water loss, which contributes to more frequent arousals from torpor, which requires energy expenditure. Essentially, the bats are burning more calories from a limited supply of body fat. Many of the dead bats found on the land appear emaciated, so like they've starved to death. And further evidence comes from biologists who observe these starved bats emerging too early from hibernation, likely seeking food resources. So this is a figure showing where white nose syndrome is now, and the red X marks the first detection in February 2006 in New York. The fungus is found in Europe, as I said earlier, and we still don't exactly know how it arrived. The colors show the timeline of spread from that point. So the blue and purple are older to more recent detections, which are red and orange in this figure. The figure also distinguishes between identification of the fungus versus identification of the disease, which can lag 1 to 2 years behind detection of the fungus. So when our study began, fieldwork in the fall of 2017, the fungus was for the most part not yet detected in Western states, with the exceptions of detection and a jump to Washington State in the spring of 2016. So this figure shows the higher diversity and richness of bat species found in the West, as well as the distribution of DoD lands. So the darker the purple, the more species richness, and the DoD lands are the kind of bright blue color. Moreover, there are unique aspects of Western geography, climate, and biodiversity that make conserving bats in the face of white nose syndrome in the West an especially difficult challenge. These include the wide dispersal of Western bats on the landscape, the lack of large winter aggregations in Hibernacula, which have been the main focus of Eastern species surveillance and research. And historically, Western species and populations are less studied than their Eastern counterparts. So in general, we have limited knowledge about their ecology, physiology, distribution, as well as hibernation. So you combine all this and it makes it much more challenging for land managers to respond to this impending threat. So diagnostic symptoms of white nose syndrome have primarily occurred in hibernating bats, but notably hibernation alone is not a sufficient predictor of white nose syndrome vulnerability. So I've listed the 3 species that have been highly impacted among 13 that are known to have diagnostic symptoms of white nose syndrome. And the pathogen can be found on another 6 species that appear to have not developed white nose syndrome disease pathology. Therefore, we really need a clearer picture of what is happening during hibernation to help predict which Western bats are going to be vulnerable and in need of management support. So to address the DoD's request to evaluate white nose syndrome as a pathogen of Western bats and to build a model framework to inform wildlife management, our objectives were as follows. We wanted to collect robust morphometric, bioenergetic, and Hibernacula environmental data on up to 5 Western North American bat species, representing different hibernating behaviors and geographic settings at 3 to 5 sites each year. We then conducted empirical analyses of that data and modeled the bioenergetics of hibernation and examined the transferability of a mechanistic white nose syndrome bioenergetic survivorship model, which was based on host, pathogen, and environmental characteristics that had been developed for bat species affected by white nose syndrome in the East to a set of 5 representative bat species found in the West. And as a final step, we developed approaches that integrate this mechanistic white nose syndrome bioenergetic survivorship model with species distribution models to evaluate the presence of white nose syndrome with climate change scenarios. So on the environmental side of our approach, we leveraged data collected from our field sites and a lot of data from external sources. So these included data from sensors to record temperature and humidity locations inside and at the cave or mine entrance, as well as data from nearby weather stations and spatial climate records. Those local scale measurements made inside and at the cave surface were then linked to regional climate products that helped us to make better models. Much of our spatial data workflow was using Google Earth Engine, which allows us to manage landscape variables at pretty high resolution over large spatial extents. So when we did our spatial modeling, we were working at 1 kilometer or so. For the 2050 climate scenario, we also used NA Cortex data. I want to point out this was a really useful resource. NA Cortex was a SERDP ESTCP supported effort to provide climate change scenario data and guidance for North America, and it's intended for just these types of analyses. Now, a big part of our objective was simply conducting the fieldwork to get baseline data because the data on the bioenergetics of Western bat hibernation just didn't exist. And I can't cover everything today, but I'm going to focus on the main elements and share some images from the team in action. The first upper left image there is of our portable energetic research laboratory, which I'm told is French for trailer. And we drove this trailer all over the West during 2 fall and 3 winter field seasons. The portable lab equipment allowed us to non-invasively collect bioenergetic data on site. We were still handling bats, just not inserting invasive probes. We eventually brought the lab to the bats, and the combination of best practices with expert bat handlers resulted in no bat mortality during our study. Below you can see Katie and Nate, our 2 postdocs there on the left, setting up the respirometry machine. Up to 14 bats hang in jars inside black coolers, which are there on the bottom shelf. And respirometry gives us measures of torpid metabolic rates, as well as evaporative water loss. Bottom middle is a picture of Kirk, our field tech, running a quantitative magnetic resonance, or QMR machine, which does a non-destructive, non-invasive 2-minute scan and tells us the fat mass, lean mass, and total body water of each bat. At a few sites, we deployed acoustic roost loggers, which monitor daily bat activity by detecting their flight calls to determine when hibernation started and ended, and that period is what we defined as winter duration. And to round out our host data, we also scoured the literature and repositories for records of winter bat occurrence and winter duration. Now, the mechanistic model of hibernation uses our field data, telling us how much fat these bats have to start the hibernation, how much or how quickly they burn it in torpor, and when they're hibernating, and their rates of evaporative water loss. So the model builds on an epidemiological triad model of disease causation. So the modeling the impact of the host and the pathogen and the environment. And our host and environment data complements the existing pathogen growth data, which are conducted in laboratory studies. So we then use basic biophysical relationships and mathematical equations, represented by my lightning bolt there, so you don't have to read them, to create a mechanistic prediction of bat survival, or the number of days until they run out of fat for healthy or infected bats. So this is an example of the bioenergetic model output showing bat survival in hibernation. So the number of days that they can hibernate until they run out of fat. On this figure, we have temperature on the x-axis and water vapor pressure deficit on the y-axis in kilopascals. So that means the difference between the amount of moisture in the air and how much moisture the air can hold when it is completely saturated. So 0 kPa along the bottom there is fully saturated or 100% humidity air. In the parameter space, what we're estimating is the days until fat exhaustion for a bat at all these different combinations of temperature and water pressure deficit. These brighter yellow colors, which you find down along the bottom, indicate temperature and humidity combinations where bats survive longer than the darker colors. The bold line is the approximate 6-month predicted duration of hibernation at the site in Montana, where bats were used to parameterize this particular model. So this means bats at this location need to have about 180 days or more of fat on board. For example, a bat hibernating at 5 degrees Celsius and 0 kPa can survive much longer at over 300 days than the same bat hibernating at 5 degrees Celsius and 0.5 kPa. So if I can point that out, so it's like the difference from up here down to about here. So the healthy bats are on the left, and in the figure, the virtually infected bats are on the right. Mechanistically, within the model, the growth of the fungus is increasing the evaporative water loss of the bats, which causes them to arouse more frequently. And this results in bat survival duration declines considerably across the parameter space. Of course, in addition to the modeling, we've also done the empirical analysis of all the field data, which is coming up in just a moment. So this slide shows how bat survival, shown in the bottom middle, is then integrated as a predictor variable into the overall spatial modeling framework. So bat survival is used as a predictor of bat distributions along with other spatial variables and attributes in probabilistic ecological niche models that use likelihood-based and multi-model inference techniques. So this approach allows us to estimate probability of occurrence. And is designed so that we can input future climate condition values into the bioenergetic models, allowing our survival predictions to be updated to those future conditions so that we can spatially predict future scenarios of both white nose syndrome and climate. So to recap, we targeted 3 types of data: morphometric on body mass and size, physiological on metabolic rate and water loss, environmental data on temperature and humidity. We then built out and parameterized a bioenergetic survivorship model and generated integrated models to predict future conditions of white nose syndrome and climate change. Here are a few more images showing the team working under field conditions. And together, these teams and others not pictured conducted the 24-hour respirometry protocol, which if we strung all of those runs together would roughly be 2 months of nonstop effort. After all of these bats were released and the dust had settled, we were thrilled to have a data set with 13 different species. So this table shows the breakdown of species and how many individuals were measured for morphology shown under the column labeled all bats, and the number of bats that provided good respirometry data under the column marked respirometry. And I've marked with an asterisk which species are known to occur on DoD installations in the West. In total, we incorporated over 3,000 bats, including 506 measured with respirometry. We were able to analyze Crinorinus townsendii at 6 different biomes and analyze Myosis at 3 different latitudes. These 2 species would allow us to further contextualize issues of sampling specific populations and our ability to generalize findings from other species across this large region and across their large ranges. So first, let's look at interspecific hibernation physiology, or variation within a species. This is a figure of temperature versus torpid metabolic rate at each of these temperatures. We had data from 20 to 40 bats per site. Our linear mixed effects model showed there was no difference in these values between these very dispersed sites. The take home is we find no intraspecific variation in Meiosis diffugus for torpid metabolic rate at 3 sites spread across this large latitudinal gradient. This was counter to some of our initial hypotheses and is actually pretty interesting. So from Montana up to the edge of the Northwest Territories, these bats are using the same minimum torpid metabolic rate at temperatures of around 8 degrees Celsius to down to about 2 degrees Celsius and possibly colder, but we didn't measure that. Likewise, for Crinorinus townsendii, we found no effect of different environments. Here, the p-value for site differences was about 0.2, based on data of 10 to 47 bats per site. While these sites were not distributed along that clean longitudinal gradient, or latitudinal gradient, excuse me, the sites represented very different biomes in the West. So it was really interesting that we observed no interspecific differences in physiology, even when comparing arid Nevada sites to humid sites in British Columbia and Southern Oregon. Now, looking at evaporative water loss from Meiosis diffugus, we did see similarities across sites, with the exception of the site in Montana, which is the light gray bar in the chart. But the difference was relatively minor from a biological standpoint. And the temperatures having minimum rate of evaporative water loss was 5 and 8 degrees, and these overlapped with the temperatures having minimum torpid metabolic rate. For evaporative water loss, Crinorinus townsendii, here, what we see is no difference among sites, except one pairwise difference between British Columbia and Colorado. So evaporative water loss is slightly lower in British Columbia, but sites here have been combined just for visual simplicity. Minimum evaporative water loss was measured between 5 and 8 degrees Celsius, again aligning with the temperature range for minimum torpid metabolic rate. Now shifting gears, let's look at our interspecific data, that is differences among species. So here is the temperature versus metabolic rate plot for Tiderata brasiliensis. We tested all 13 species over a range of temperatures, and some species like Tiderata, illustrated here, clearly don't like the lower temperatures. They get a little grumpy. This is a plot of temperatures, again, versus metabolic rate. And over the range of 8 to 12 degrees Celsius, we get the low metabolic rates that are indicative of torpors over here on the right. But below that, the bats aroused, and you can see they clearly were not remaining in torpor. We saw similar arousal responses to low temperature in Myotis evotis, Myotis physinoides, and bolans. However, most of the species we tested were pretty broadly tolerant to a wider temperature range, as illustrated here with the same plot for Myotis humanensis, where most of the individuals remained torpid across the whole temperature range. Which isn't to say that these bats aren't affected by temperature. Of course they are. If we zoom into just the low metabolic rates during torpor, you can clearly see the range of temperatures that results in minimum metabolic rate. You can also see the increase in metabolic rate below the minimum defended temperature, which in this case is somewhere between probably 2 and 4 degrees Celsius. You can see this step up here. Visually, there is clearly a range of temperatures where torpid metabolic rate is minimized. So we then used post-hoc pairwise comparisons to map out at what temperatures each species of bat uses a minimum torpid metabolic rate. As you can see on this figure here, just visually, you can see that's 4 and 6 degrees Celsius. So that's what we're summarizing here in this plot. In the middle, you can see the Myotis humanensis again. So that's the one we were just talking about right here. And the temperatures we measured are in gray, and the temperatures where we observed minimum torpid metabolic rates are shown in black. The asterisks highlight cases where the range reached either the upper or lower limit of the temperature range we tested. So again, for UMAs, we measured them between 0 and 8 degrees Celsius, whereas most other species were measured 2 to 10 degrees Celsius due to slight differences in respirometry protocols from some older data that we brought in. So some bats, like Aptescus fuscus and Myotis ciliolabrum, can sustain a minimum torpid metabolic rate over a wide range of temperatures. So those are these guys right here. You can see they're end-to-end. They're able to do it. Other bats like Perimyotis subflavus, Myotis volans, and Myotis humanensis have much narrower ranges of temperatures. Some bats hit their minimum defended temperature at 8 degrees Celsius. Others don't reach it until 2 degrees Celsius or possibly even lower, which is pretty cool. The other really interesting finding was that bats group into high and low rates of evaporative water loss. The bottom group in light blue has a significantly lower rate of evaporative water loss compared to the upper group in dark blue. The group of bats that has a lower rate of water loss is able to hibernate in drier roosts, whereas the group with higher rate of water loss tend to roost in more humid sites, thereby reducing their overall water loss. So you'll notice the high evaporative water loss group includes species that have been listed because of white nose syndrome, like Perimyotis subflavus, Myotis oesophagus, and the low evaporative water loss group includes species like Aptescus fuscus and Crinerinus townsendii, which have been less impacted. One other thing to point out is that Lano there on the bottom, or Lasiodicterus noctivigans, may actually represent a distinct third group, but for now we've conservatively only reported 2 groups. In reality, it could well be a whole continuous spectrum, but we would need more data from different species to address that. We'll come back to this as other lines of evidence are suggesting evaporative water loss may have a bigger impact on white nose syndrome susceptibility than is currently appreciated. In summary, of course, bats do different things. This provides us a better indication of how temperature affects hibernating bats. That is, what temperature range is most conducive to not using energy quickly. Among other physiological necessities, bats may try to optimize midwinter. Last but not least, we see a big difference in terms of how different species manage water loss, and this might offer insight into why some hibernating bats are more susceptible to white nose syndrome than others. So that wraps up the empirical findings that I have time to show you today. In conclusion, we found no significant evidence of intraspecific variation in two key parameters of bat hibernation energetics, torpid metabolic rate and evaporative water loss. There was no variation in torpid metabolic rate, and for the most part, no variation in evaporative water loss in Western species, in these two Western species. On the interspecific side, we observed differences in rate of evaporative water loss, which may be a good risk factor for white nose syndrome mortality, as the groups roughly align with known white syndrome mortality patterns. We also observed difference in the temperature range of minimum torpid metabolic rate. Lastly, we did find similarities for minimum torpid metabolic rate, suggesting that minimum torpid metabolic rate is not a useful risk factor for white nose syndrome mortality. One of the big takeaways is we went into the study thinking torpid metabolic rate was going to be a key factor that could help us differentiate white nose syndrome susceptibility among bats. What we found is that it really didn't matter much within or even between species. Instead, it appears evaporative water loss is what may help us separate out at-risk species, as at least empirically, it seems to group out with different white nose syndrome outcomes. More to follow on this aspect in the modeling section, as all in all, evaporative water loss appears to be a key driver of white nose syndrome susceptibility. So our study included 13 species of diverse bats that cover a wide range of hibernation behaviors and our physiology and different physiology as well across Western United States and Canada. Some of these species, like Myos lucifugus and Neptuscus fuscus, have been the focus of previous study, but there has really been very little hibernation research on many of the species in our study and practically nothing in the West in general. The data collection effort alone was a huge contribution to bat conservation. Moreover, the baseline data would not have been collected if it were not for the study, and similar studies will be very challenging to conduct moving forward because of restrictions that come with species listings and the presence of the fungus now in Western locations. So the lack of local bioenergetic adaptations is actually a really big finding. It means that we don't have to spend a lot of time and effort to measure bioenergetics at different sites and in different biomes to have confidence in the interpretations. And this gives us confidence that we and others can use the bioenergetic hibernation data from a species at one site to make inferences across the range, of course, with some appropriate caution. With respect to white nose syndrome threats, it suggests that from a solely host bioenergetic perspective, we would not expect significant variation in a risk factor like evaporative water loss across the species range. So physiological responses across a range of temperatures also provide some indication of the conditions that may be preferred by each species. Again, our study was the first to measure and assess this across species and sites. And from a physiological standpoint, it's just fascinating that some species tolerated temperatures that approached freezing. There's an important caveat here that people should keep in mind is that we didn't actually measure these conditions in situ. We measured them in a mason jar, but that's the best anybody is going to be able to do with available technology. So our finding of differences in evaporative water loss in Western bats and species known to be impacted by white nose syndrome suggests evaporative water loss could be used as a potential white nose syndrome risk factor for different species, which leads us into the second part of the talk on using these data to parameterize models to assess the interaction of host physiology with the environment and the pathogen. So with that, I think I get to open the floor to Q&A session number 1. Thanks for your attention thus far.
Thank you, Sarah. We're right on time. We got a number of questions that have come in, starting with this first one. How did you select the sites that you included in your study?
That's a great question, and it was a big challenge. We had, when we put out the proposal, kind of scoped out where we could find large numbers of hibernating bats, and a big part of that was reaching out to state agency partners and biologists familiar with research on Western bats. We reached out as well to a lot of DoD installations and consulted a lot of reports on what bats had been seen where. And then we also had to look at a matrix of and filter by winter accessibility. And that involved a lot of conversations with state managers, as well as a variety of different DoD biologists, as well as the National Park Service managers. At that stage, we didn't know if there was going to be local variation or variation between fall and winter measures for even that matter. As it turned out, we don't see local variation in torpid metabolic rate or evaporative water loss. So our findings should be applicable to populations of these species found on DoD lands, taken with appropriate caution. I think one of the challenges was it came down, we just needed to be able to get our hands on good numbers of bats so we could reach, we could do some statistical analysis. But, large hibernacula out west are kind of the outlier. More common is bats using more distributed kind of hibernation sites, so cracks and crevices in different geological features. So that's also, I think, one caveat to keep in mind is we're working with populations that are using these cave and mine sites, but bats may be using different sites out west. However, if they're experiencing the same conditions, so if bats are selecting the same sites that bats selecting caves that they would in like a crevice, then our model would also be applicable. But there's increasing work on this, and people are getting out there and measuring some of these cave and crevice sites for their microclimate conditions. And with that information, we could also apply this model to what the bioenergetics of a bat hibernating in that cave or crevice site would look like. So in sum, it was a big effort. Lots of folks got involved, and it came down to where we could get large numbers of bats and where we could get winter access. And that's the kind of the sites that we ended up with.
Great, thank you. This is a question from one of our attendees. Do you know if any endocrine factors, for example, like cortisol, have been evaluated as potential risk factors for the white nose syndrome?
Yeah, there is some work that has looked at immune function and differences in species with respect to immune function. There's some work that came out recently looking at how some bats have a more localized response and others have a more systemic response. When it comes to stress factors and other response, I don't know if I've seen any in particular, but it is another kind of space I think we need to keep our eyes on. As I've said and tried to be specific, our work is just kind of focused on the bioenergetic aspects, but we're not looking at these other factors like, as mentioned, like endocrine or immune factors that may also come into play with respect to risk factors and who's going to be, figuring out who the winners and who the losers are going to be once this is widespread across the West.
Great, thank you so much, Sarah. We have another question. Can you address what you meant by no biologically relevant difference of evaporative water loss within species?
Yeah, so our respirometry protocol at these temperatures used a stream of dry air to avoid potential condensation at low saturated water vapor pressure that's associated with low temperatures. Basically, running humid air would have gummed up the system of tubes and sensitive measurements and all the instruments in that. It's like a $100,000 machine. We don't want to break it. And this dry air likely contributed the small little variation that we noted between the most northern and our southern Crinoranus tanzendii and Myotis lucifugus sites. And these guys would typically hibernate in select conditions with more moderate to high levels of humidity, respectively. So the variation we observed in these populations also didn't move them out of that high or low evaporative water loss group classification I showed you in the last slide. We looked at that. And we think, or at least we surmise, that by testing in such dry conditions, we may have kind of detected these really subtle phenotypic differences because of reduced gene flow at the extreme distances of the populations that we were comparing, but they probably have no biological consequence at present, at least.
Thank you. And a related question, to what extent can the evaporative water loss rate results apply to other species of interest?
Yeah, I think that's a great question. So I think and the modeling will maybe point a little bit to that answer in a moment, so I won't try not to give that away. But I think we see this strong grouping. If you were to go out and measure some additional species that we didn't do in this study, the first check would just see which group they fall in on that spectrum, whether they create a new group or if they group closer with bats that are highly susceptible to white nose syndrome, or if they group with other bats that are showing more or not as much impact. That would be an initial indicator of risk for that species. So measure a bat and see what its evaporative water loss. If it's a high evaporative water loss bat, and I'll show you in a moment another risk factor, then it probably is indicated that this bat is going, and with other, we got to figure out, in the context of where this bat also selects to hibernate. But that would be an important risk factor that would indicate whether or not that bat would be susceptible to white nose syndrome.
Thank you, Sarah. And one last question before we let you complete your presentation. You talked about collecting quantitative magnetic resonance data. How did body fat specifically vary within and between species?
That's a good question. So my colleague, Liam McGuire, offers his TOR machine as an add-on to this project. And one of the lessons learned, I think, is the portable unit that we used was really sensitive to temperature and required really stable conditions because it's basically just a large magnet. We did get good data for our Oklahoma site where we moved the machine into kind of an adjacent lab building, which was also really close to the site, and a couple of our Nevada sites, but running it out of the trailer at the other sites resulted in less reliable measurements. And we do have a manuscript and review that looked at some of our Oklahoma and Nevada data. And we show males in the Oklahoma site put on more lean mass than the females, with lean mass contributing about 18% of the female total mass gain compared to 18% of the female total mass gain and 35% of the male mass gain, which has important implications on several aspects of hibernation physiology, including
It would appear that we've lost Sarah, so just please give us a moment until we get her back on the line. Just a moment as we try to get Sarah back on the line. Kurt, while we're waiting for Sarah to rejoin, would you mind answering some questions as they relate to the RC program and similar funding efforts that are ongoing?
No, that'd be great. Go ahead.
Excellent. All right. Let's see here. So what are some other endangered species on DoD lands that SERDP is trying to study and come up with mitigation efforts?
Yeah, great question. In fact, one of the things I'd like to highlight for everyone on the call today is that yesterday the new calls for proposals for this year just came out, and so I would invite everyone to come to the SERDP website who has an interest in the work we're doing. Sarah, are you back with us?
Yeah, sorry, I paused. I thought somebody else had dropped, and then I realized it was me. I'm somehow my phone, I don't know what happened. It just cut me off.
Yeah, well, let me just finish up by, I was just sharing with folks while we were, and first off, great talk, absolutely great talk with great information. So I'm really looking forward to the second half. First half has been absolutely wonderful. But anyway, I was just sharing with folks that the SERDP solicitation for this year is out, hit the streets yesterday, and there are two statements of need that are coming out of the Resource Conservation and Resilience program. One is focused on threatened and endangered species in response to multiple stressors for TES species. And then the second one has to do more with insulation infrastructure, having to do with saltwater intrusion, which the community right now probably wouldn't be quite as ramped up about. But yes, there is a brand new call for proposals that hit the streets yesterday that I would certainly invite everyone to take a look at. And to your question, Rula, a couple of the species that are listed on that statement of need are the golden cheek warbler, the streaked horned lark, the leaf-spells vireo. But I want to share with folks that this statement of need is not limited to those species. It's those are just used there as examples. So, without further ado, I will turn it back to Sarah. Thanks.
Thank you so much, Kurt. Sarah, let's go ahead and wrap up your presentation, and we'll get to the additional questions that are coming in towards the end. Please proceed.
Excellent. Thanks for your patience, everyone. Okay, so let's get back in the flow. So this slide is here to help orient you to our key modeling steps, which are linked to various manuscripts that are published or currently under review. We were building off that published bioenergetic survivorship model, which I'll refer to as the Heyman model, that had focused on 2 eastern species and 2 species from Europe. It was a really good foundation, but we saw room for critical improvement. The first improvements were to the survivorship model itself, and it included replacing the cooling submodel with a more accurate submodel based on first principles. We also added fungal growth and evaporative water loss to the model using Meiotis fucus to validate those refinements. Then once we had collected and cleaned our field data, we were able to parameterize the model for 9 Western bat species. And then the next chunk of modeling work generated spatial layers of key bioenergetic parameters that built off different observational data sets. So the results were models we could use to generate spatial layers of cave and mine temperatures, body mass and fat of Meiotis fucus, winter duration, and winter distributions of Western bat species. So these spatial layers really kind of pushed the science forward on bat ecology and physiology, and were also used to estimate white nose syndrome survival, with one focused on Meiotis fucus and another looking at interspecies projections and the impact of climate change. So these last 2 chunks of efforts, generating those spatial input parameters or attribute layers and spatial predictions of white nose syndrome survival, build and really borrowed extensively from each other. Because this all builds on that survivorship model, I'm just going to give you a quick reminder of how that works, and I'm going to skip the biophysical equations. But the model accounts for the impacts of the environment, the host, and the pathogen during hibernation in terms of the fat consumed. It's a fat tracker model, basically. And the arousal torpor cycle of bat hibernation is built into the model, and it's broken into the 4 parts of that process. So there's equations that account for the energy required for the bat to be in euthermia, the energetic cost of cooling, the energy that the bat uses while in torpor, and the energy required for the for the warming back to euthermia. So torpid bats have a very slow rate of fat loss compared to aroused bats. In fact, overall arousals account for 90% of a winter fat budget. Being warm and warming up in a cold space just burns a lot of fat. And the infected bats, again, have more frequent arousals, which leads to greater fat loss overall, and why the infected bats appear to essentially starve before winter is over. So if you want to see the equations, see Haas et al. 2019 paper, and there's one of the last slides. You can click to our website, and on that page, it'll take you to the paper itself. So as a first step to build our own bioenergetic white nose syndrome survivorship model, we dug into an existing model, that Heyman model, and made some key refinements. So the first one was that towards that submodel that was used to calculate cooling costs. So time is not to scale in this figure on the left. A torpor duration is typically 2 weeks or more, and arousal durations usually last a couple of hours. But we just spread it out here so you can see the different parts. And as you may recall, the arousal event consists of rewarming, time in euthermia, and then cooling back to ambient conditions. So the Heyman cooling submodel was originally was just focused on that cooling aspect, and it was originally relying on an assumption that cooling costs are 67% of warming costs based on a study that was done at Richardson's ground schools. And that study has been cited and used in 10 studies on bat hibernation. However, hats off to our team's astute postdoc, Dr. Haas, who realized this was way off when she was just thumbing her way through the model and getting familiar with it. And she built up a new submodel that used first principles, and she verified it with external data. And it turns out that the original Heyman cooling submodel and all those other studies that had used it were overestimating cooling cost of bats. So it's shown in the blue triangles over here. You can see Richardson's ground squirrels are there. So she published this finding last year in the Journal of Thermal Biology. Other big refinements were the addition of evaporative water loss and fungal growth terms and interactions. We used observed values of evaporative water loss, fat loss, and torpor bout duration from Myotis leucocephalus to then validate our advanced model. Just the first two are shown here. So in these plots, the measured value is on the y-axis, and the modeled value is on the x-axis for these two parameters. And the dashed lines represent what would be an ideal one-to-one relationship between the measured and modeled values. The solid lines here represent the fitted relationship, and the shadow is the 95% confidence interval. Basically, there's no significant difference across the three parameters that we used to validate this model. And then we did a sensitivity analysis, and it also shows that host factors are now most influential, which wasn't the case of that Heyman original model. That sensitivity analysis also showed that the rate of evaporative water loss was a significant predictor associated with survival. So here again are the survivorship predictions for little brown bats at the site in Montana that I introduced in the method section. The healthy bats, again, were predicted to survive for over 360 days in the microclimate that they currently select for roosting. However, when you introduce the fungus and white nose syndrome, almost all of the microclimate conditions available at the field site resulted in mortality. Again, winter duration at the site was about 180 days, and bats are selecting the saturated environments that were within the temperature range that allowed for a lot of fungal growth, resulting in increased energy expenditure and ultimately shorter time until fat exhaustion. There are some microclimate conditions that would permit survival at this site, but these locations are not being currently selected by any healthy bats at the site. So unfortunately, these hibernaculum temperatures and input parameters are also comparable to the hibernacula that are inhabited by highly impacted Myotis leucocephalus populations in eastern white nose syndrome affected regions. There's a small bright spot here, and that is there's some preliminary data in the east suggesting that if persisting bats of this species may actually be shifting to cooler locations when they're hibernating, which corresponds with our predictions here that, if bats are going to survive, they're going to have to figure out how to find those colder spots to hibernate. So the interspecies white nose syndrome analysis was similarly, so we focused the model on Mytocystis, and then we shifted to basically doing the same model at all these different sites with different species. So this interspecies white nose syndrome analysis was parameterized with our field data and our estimates of winter duration, which I'll get to momentarily. So here we were able to evaluate 9 species across 8 different sites, which nearly doubled the number of targeted species that we set out in our proposal. The simulation, I'm just getting a warning that my computer battery, oh, there we go, pardon me. So the simulation model tracks each individual bat's energy use as it goes through cycles of torpor and arousal, and it accounts for these traits and conditions that contribute to white nose syndrome survival or death. So for this study, what Katie did is she ran the model for 100 bats of each species over 100 winters, and she drew from the population distributions for each of those species. So the take home will be if a bat exhausts its energy resources before winter is over, it's going to be marked as a mortality. Conversely, if the bat has energy to survive through winter, we mark that bat as a lucky survivor. So here are our predictions of white nose syndrome survivorship. The figure shows the differences between predicted days until fat exhaustion, and predicted winter duration. And those bars, are standard deviation bars. Positive values are on the right, and those are good. So those are above 0 in survival. Bats are living longer than winter duration. On the left are the negative values, and these are the bad outcomes. Winter duration is longer than the bats could energetically survive. So we find Paramyotis subflavus and all the small Myotis species, those with less than 10 grams on average, or the bottom 5 on the figure, were predicted not to survive. Among the bottom 5, there was actually no significant differences in predicted survival. Bats predicted to survive were Myotis bellifer, Carinarhinus townsendii, and Aptuscus fuscus. So these are bigger bat species that are adapted to drier environments and had higher survival than those that are adapted, as you can see below, that are hibernating at near saturation. So the saturated conditions are, again, typically used by smaller bats, like those that are shown at the bottom of the figure, those bottom 5. And these are, again, when these smaller bats use these saturated conditions, it's less energetically costly for them for healthy individuals, but they lead to greater fungal growth and thus higher white nose syndrome mortality. So the takeaway suggests there's a trade-off here between water conservation and fat conservation in regards to white nose syndrome. So as I mentioned in the model orientation, to make better spatial predictions, we needed to kind of step back and generate some spatial input layers of key parameters and attributes. So the central aim of one analysis was to quantitatively test what had up until now been pretty much a qualitative description of relationships between subterranean temperature, mean annual surface temperature, and various site attributes. And this had been, qualitatively done in a paper in Perry 2012, but we were changing this into more of a quantitative framework. So to do this, we used, to our knowledge, what is the largest set of available climate and microclimate data compiled to date, at least for the West. There may be some other stuff out in the East, but I haven't seen it. And the temperature data was collected from 75 caves and 64 mines across Western North America, covering 9 U.S. states and 2 Canadian provinces between 2006 and 2019. So I'll just leave you with the 3 takeaways from this modeling, and that was we found what we expected to find, a positive relationship between mean annual surface temperature and subterranean temperature, a positive relationship between subterranean mean temperatures with increasing distance from site entrances. So the deeper you go into a cave or mine site, the warmer it's going to be. And finding that mines tended to be warmer than caves, likely due to airflow and the number of openings. So the qualitative review predicted these same relationships, and we just went back and verified them quantitatively. And here the figure shows the model predicted windows of hibernation suitable temperatures, so between 2 and 10 degrees Celsius for caves at depths of 50 to 100 meters. And that's the one in the upper left. So the caves are right here. And then on the right you can see are the same as predicted for mines at those same depths. And then below that, because we did want to see if we're actually doing an improvement, some folks had used, a couple models had used mean annual surface temperature, and that's kind of the state of the science when we started. So we can compare that with the performance of those two figures on the top with the figure on the bottom. And these maps help illustrate really the improved performance of our new model compared to mean annual surface temperature alone. In the figures, you can see in the black here, we've masked where temperatures of 2 to 10 degrees Celsius, this is again where vespertilinoid bats tend to hibernate, are not found. And this is in the key kind of months of December to February. So notably, our model more frequently predicts suitable conditions at known hibernacula in Alberta and Texas. So we do know there's bats up here, even though the map isn't predicting it. And we do know there's suitable, and we do find bats down here using these temperatures, even though this model isn't finding it. So we know they're there, but we're improving on the model, and it's nice to see. You can see we get larger coverage up here into Canada with our model of mine temperatures as well. So, oops, jumped ahead there. Further parameterization of the model with species or even guild-specific hibernation information can provide an estimate of region-wide potential suitability of hibernaculum conditions under present or future climate. We did look at modeling humidity, but these sensors have typically failed in really high humidity environments, and there just wasn't enough of existing data to model it at this scale. So let's look at another key spatial layer. Here we're focused on Meiosis diffugus due to the high impact of white nose syndrome on eastern populations and just the greater availability of published data and its widespread distribution. So our results suggest that there's substantial improvements can be made in the estimation of hibernation duration, and this can be done by including elevation and the number of days with frost. Latitude was in there. It wasn't a significant predictor, but it did improve model performance. So we anticipate that probably just a series of complex interactions between surface features like slope, aspect, elevation, and suitable crevices, or cave features itself, the entrances, airflow, and depth that we just can't quantify. So it is kind of a simplified model that would ultimately define when and where suitable hibernacula conditions would exist and how long these bats would be using those conditions. But it's a good approximation, and it's a significant improvement from what we had before at this scale. Next, spatial observations of body mass and fat mass were used to model these factors across the range of Meiosis diffugus. So taking observations from a couple studies and then projecting them spatially. And we made a relationship, so fat mass was calculated using a linear equation scaling relationship that we identified between pre-hibernation fat stores and body mass. And for this, we assume that the lean mass of bats generally stays consistent, while the difference in body mass is probably due to increases in fat. So our model selection suggests that variation in the duration of winter hibernation may in part drive variation in both body mass and fat stores across the range of the species. The relationships between mass and thus fat and latitude and days below freezing also suggests stronger selection pressure for heavier bats in the more extreme conditions, which is what we also see empirically. So another key spatial layer was mapping the winter distribution of Western species. In other words, where do species hibernate? This slide shows the predicted relative probability of occurrence of Crinoranus townsendii on the left, Meiotis californicus in the middle, and Perimyotis subflavus on the right across their ranges. We have also run these analyses for Meiosis diffugus and Bellifer, which are on the next slide, which I'll get to you in a second. Because bat winter distributions in the West had never been modeled, we used boosted regression trees, a method that allows kind of a flexible and for nonlinear relationships between predictors and relative probability of occurrence. So this approach relates the survival capacity estimate along with key landscape attributes to bat occurrence. data, and it's really a kind of a hybrid correlative mechanistic approach, as I explained in the method section early on. So for each known occurrence location, we had selected 3 random background points, and these are selected to allow us to calculate the relative probability of occurrence. You can see here we've overlaid the species current IUCN range extents, that's the light turquoise outline, and winter occurrence locations used to fit the model are overlaid. Those are also the turquoise points. Occurrence probability is scaled to reflect the fact that predictions represent relative occurrence probability. So the yellow areas of the maps represent the 10% by area of the map landscape with the highest occurrence probability. So more likely in the brighter areas, less likely in the darker areas. So here are the maps from Meiotis diffugus and Bellifer. To our knowledge, no one has ever created winter western distribution maps for bats, and this really actually surprised me. Those current IUCN range extents are simply hand-drawn ranges, circling areas around known observations. So there's clearly here an improved understanding of where bats hibernate in the West, and the conditions that create suitable hibernacula is critical for DoD land managers to anticipate and address the conservation needs of white nose syndrome susceptible species. And these maps are an important contribution because we're starting to fill what was a huge knowledge gap in this space. So let's dig in a little bit more to the final predictor influences from that boosted regression tree models, estimating the winter species distribution of bats. And on the left, you can see the 5 species that we modeled, and along the bottom are the attributes. So these are the species, these are the different attributes that came into the model, or at least that were included in at least one model. Note, we also derive predictors at multiple spatial scales because the scale at which bats perceive and respond to the different landscape attributes may vary among species in specific attributes as well as locations. So brighter colors here indicate a higher influence of that attribute or predictor. And predictors that were dropped from a given model are shown in gray. Variables are ordered by their average influence across species, decreasing from left to right. So on the left, you can see ruggedness, or bottom left there, topographic position, and percent tree cover were among the most consistently strong contributors based on mean relative influence across species. Winter survivorship, on average, also had high influence. So again, winter survivorship is coming from that bioenergetic survivorship model. And its influence did vary considerably across species. In contrast, karst, which was a presence-absence variable, had the lowest influence overall, which was interesting. But again, we're focused here on the West. And we do know bats are using more distributed sites, not just caves and mines. But do note it was not considered in Meiotis diffugus because we did not have data on karst in the Canadian portions of its range. As you can see, the shape and relative importance of these relationships vary among species. Take, for example, distance to mine. It was really important for Crinoranus townsendii and Meiotis californicus, less so for Bellifer and Lucifugus. Of the neighborhood sizes compared, typically moderate to large neighborhoods, so 5 to 20 kilometer diameter, tended to capture the scale at which bats responded to landscape attributes better than a small neighborhood, which was set at 500 meters. But the scale of selection for each attribute did vary among species. So our findings here point to ranges of landscape attribute values where each focal species may be most likely to hibernate, and they highlight the importance of protecting mine features as hibernacula for multiple species. Importantly, our findings indicate that topographic attributes are important predictors of hibernaculum selection, suggesting that winter bat occurrence, something that happens underground, in part can be predicted from readily mapped above ground features. We also found that our mechanistic estimate of winter survivorship contributed to a prediction of winter occurrence probability for all the focal species. And in one case, that is Meiotis californicus, you can see it was by far the strongest predictor. So here we ran the survivorship model across North America for little brown bats. Uninfected bats are on the left, and bats infected with Pseudomonas destructans are on the right. We predicted survival capacity for Myotis centrifugus hibernating at the best available temperature and 98% relative humidity. These are the ideal hibernating conditions for this species. So survival capacity in days is the color scheme there, is calculated by subtracting the maximal days in hibernation that an individual can tolerate based on the pre-hibernation bat stores. And this is subtracted from the predicted duration of winter. So again, positive values are good, those are in purple. They suggest that bats will likely survive, while values below 0, those are shown in orange, imply that the fat stores were insufficient for survival. So in the best case scenario, infected bats are mostly surviving, but their survival capacity is dramatically reduced. In the eastern areas where white nose syndrome has really devastated many hibernating colonies of the species, we note that available microclimates can actually be warmer with temperatures reaching 10 degrees Celsius, which has a significant impact on energy expenditure during hibernation. So despite this, our predictions suggest that survival may be possible in ideal conditions. So provided that bats can find and use the coldest areas within the cave or mine system. And keep in mind, the survivorship model, like all models, is a work in progress in that there are components of it that there are elements and behaviors of bats, like Hibernacula roost switching, where they'll switch roost within a cave or mine. They also take midwinter flights and arousal frequencies that would further consume energy and impact survival capacity that can't yet be modeled at this scale. So another way to look at survivorship is to just look at the percent increase in fat in infected versus healthy bats. So this figure shows that relative increase as a percent, again, under what is a best case scenario. While you saw on the previous slide that most areas remain above the mortality threshold, the increased percent of fat needed to hibernate with Pseudomonas destructans highlights the high metabolic consequences of infection on, so you can look here, on average, a bat was predicted to metabolize basically 150% more fat to survive infection. And no matter where you are on the map or within the little brown range, little brown bat range, more fat is required. Finally, we ran climate projection models for 5 species. Shown here in the upper left panel is the current relative probability of occurrence of Myotis centrifugus. Again, so that's this one up here in the upper left. Again, so the bright yellow colors on the map represent the 10% by area of map landscape with the highest occurrence probability. And on the right is the change. So this figure here on the right is the change in that relative probability of occurrence. The purple areas are showing are areas of loss. Oops, just went forward. Very sensitive keyboard. And the green areas are showing areas of increase in the presence of white nose syndrome. And generally, as expected, probability of occurrence was projected to decline following exposure to Pseudomonas destructans. And we see the greatest projected declines with Pseudomonas destructans exposure were typically in areas where the highest occurrence probability, where we see the highest occurrence probability under current conditions. So the areas currently expected to be most suitable for a given species. Below that, in panels C and D, so down here, are 2 of the 4 climate scenarios. The other 2 had similar results. I just didn't show them because the slide wasn't big enough. And the 4 scenarios were driven basically by 2 global circulation models and 2 dynamically downscaled regional climate models. As you can see, with both stressors of climate change and white nose syndrome acting on the species range, we do see some rescue effect of climate, with the purple color becoming less pronounced in these 2 bottom figures compared to this upper right figure. Now, you compare those Myotis centrifugus findings to the observed thresholding behavior here in Paramyotis subflavus. So in this figure, it's a little bit different. And in panel A in the upper left, we're looking at this current distribution, and white nose syndrome presence is actually directly below it. So that's presence and then introduction of white or current distribution, and then the impact distribution with white nose syndrome directly below it. And here I had room to include all 4 climate change scenarios. And then again, these are 2050 climate change scenarios. So you can see Parameter subflavus declines due to white nose syndrome were replaced by marked increase in occurrence probability in the southwest, or sorry, excuse me, in the southeast, that big green patch there. I don't know how I can miss it, given climate change. This thresholding behavior appears to follow and is probably driven by spatial patterns in the frost-free period. I do note across species, typically all 4 climate scenarios showed in general close agreement regarding future changes in occurrence probability, but this was the only species among the 5 that we examined that had this strong thresholding behavior. So these predictions can help managers to better anticipate the species and place specific impacts of these stressors individually and synergistically across the West. So our findings do suggest that mid-century climate changes may actually help rescue some bat populations, but that a warming climate is not predicted to shield all species in all areas. So to bring me to my wrap-up, the main findings from the second half of today's talk, main conclusions from part 2, we accomplished what we set out to do, namely assess the bioenergetic threats of white nose syndrome alone and in concert with climate change to Western species. In the process, we mapped the winter distributions of bats using surface attributes, and these surface attributes can be used to better understand the ecological requirements of different bat species. We also, in the process, derived key parameters that impact survival, including winter duration, body fat, and body mass. These resources are going to be fundamental to allocating monitoring, research, and management resources. So our development of modeling tools makes it easy to quickly assess species risk. Bats can be measured in the fall, and these measurements can be used to predict risk for species at a specific site or across its range. The code for this model lives online in a GitHub package for future use and development, and it's soon to be rolled out as an R package. We also have developed a list of species at risk that should be prioritized for surveillance and changes in hibernation behavior, namely small myota species and those with high rates of evaporative water loss. If we see shifts in colder winter roost sites, this would be a positive development. And there's some really initial genetic work by Arturi et al. Indicating bats may be undergoing genetic changes that actually help them survive this bottleneck. There is a need to protect as many bats as possible. So in addition to protecting known mine and cave hibernacula sites, we should limit nuisance take to when it's only indicated and otherwise use non-lethal means of removal from structures. Lastly, there is potential for climate change to rescue susceptible species from white nose syndrome impacts, but time may not be in our favor. So the best place to track publications is to visit our website there, where we're posting links to our publications, and all of these should be open access from the journal access page, so just click on the citation on our page. And they'll also be releasing a final DoD report on the project, which is undergoing a draft review. A big thank you to all those who partnered with us to make this study possible, and also, of course, to the core project partners and SERDP as our funding source. This is Q&A session, but there was a slide on here, but it's gone. So anyways, we're in Q&A session number 2.
Great. Thank you so much, Sarah. We have a number of questions for you. The first one came in from the Air Force. What management action suitable for inclusion in an integrated natural resource management plan can you suggest based on your study results?
So for now, I think what we can recommend is to limit nuisance take kind of as a base level. We need pretty much every species and every population that's at risk to receive, less stress. We don't know, if evolutionary rescue is going to be a feasible intervention moving forward, but it's just as feasible as some of the other more drastic interventions, such as spraying things on bats and potentially vaccinating bats. Among others. So I think it's important to kind of start locally, think about what you can do to maintain good bat habitat. I also note, I think working across federal partners. There's ways you can monitor these populations with NA bat. And there's, when we did the analysis, I just actually ran it. When you look at federal lands in the West, you know, these species ranges, federal lands account for 30 to 50% of the species range itself. So I think there are ways we can think about, you know, working on bases, maybe to help implement some of these surveillance tools so we can watch and target and figure out which species are declining so that we can do monitoring and just kind of integrate this across the West so there's kind of a proactive management response. So we don't have to wait for the bats to start dying. We can start, you know, focusing on some of these at-risk species. And if you do have these species on your site, you know, figuring out more where they might be hibernating and putting some monitoring systems in place so that we can learn from how these bats are responding once white nose syndrome arrives.
Great, thank you, Sarah. Another question. Can the models you described in this section of the presentation be used to predict which areas will be infected next on DoD lands?
That's a good question. So what we did in our models is we essentially are acting like God. We can run the models without the presence of white nose syndrome or the fungus, and then we can turn it on in the models. So we're not actually predicting the rate at which, you know, the fungus is spreading or where it's going to go. I highly suspect it's probably spread widely across the West currently. We're just not able to detect it at the levels with the tools that we have. I strongly suspect if it's not there already, it will be there shortly. I mean, within, you know, 5 to 10 years at the very minimum. So no, these models don't allow us to anticipate which sites will be hit next, but I do think it's feasible to just accept at face value that PD will be there. If it's not there already, it will be there very shortly.
Great. And as we start thinking about mitigation strategies based on the outcomes of your work, how feasible do you think it will be to target specific groups of bat species with potential mitigation approaches?
Yeah, that's the tough part for Western bats. They are so dispersed on the landscape. A lot of the tools that we have are more focused on, have been developed in the Eastern context. So, you know, where you could treat bats directly, you know, with spraying things as they come in and out of Hibernacula or treating the cave sites itself. These are a couple of options. You know, some of the vaccines that maybe bats could share among themselves might be feasible out west. I don't see that those tools coming along fast enough in the timeline that we would need them. And one of the things that our group has been thinking a lot about, given, you know, the bioenergetics suggests that there is spaces for these bats to survive, and it's just going to take a behavioral or, you know, some, behavioral or genetic adaptation for them to figure out how to do that. That, you know, this idea of evolutionary rescue should just be considered alongside, just as feasible alongside some of these other interventions. Otherwise, I don't think Western bats are going to have it, you know, some of these kind of current interventions that are being deployed are going to be applicable to the West. So I think it's kind of thinking about what can we do proactively to support, you know, a successful kind of transition through this bottleneck. We need lots of population, we need lots of diversity, we need evolution to select those winners and to then support the winners once we know where they are, and to make sure, you know, those populations that have the right characteristics are conserved, so that we don't some of these species just don't wink out at the end of the day.
Thank you so much, Sarah. And we are out of time, so we're going to go ahead and wrap up really quickly with a preview of what's coming next in the webinar series. But if you have any additional questions for Sarah, we'd encourage you to reach out to her at the contact information shown in the slides. Thank you, Sarah, for a wonderful presentation. I'd like to remind all of you that our next webinar in the series is on Thursday, November 19, and it will feature DoD-funded research efforts to measure and enhance abiotic natural attenuation under in situ conditions. This webinar will feature two speakers, Dr. Paul Trepniak from the Oregon Health and State University, and Dr. Michelle Scherer from the University of Iowa. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars through the end of 2021. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.